pretty tedious, and if the packer is a difficult one, it can take hours for the analyst to figure out. And if you have 160,000 pieces a malware that are packed, there's pretty much no way you can manually unencrypt them all. But once you get it fully deobfuscated, this is basically what it looked like in IDA Pro. You can see the imports, you can see strings, you can see internal functions to the binary. So I'm going to show a quick demo of the manual process. Okay, so we're going to take an actual piece of malware here called netbull and detect what it's been packed with. It's been packed with UPEX in this case. So I'm going to execute it here to prove, yes, it's actually a valid running process. It opens up a TCP port and see the Windows firewall detected it. So the next step is I'm going to dump this into IDA and see what I see what it looks like. What can we tell about this before we try to unpack it? IDA's going to analyze it, load it up, and basically what you're going to see is it's been obfuscated. The names window is pretty much empty. There are no internal functions available to us to look at. The imports table is pretty limited. It's very rare that a binary actually has that few imports. So pretty much we can't tell very much about this binary. We need to deobfuscate it. So the easiest way to do that, UPEX is pretty simple. We're going to load it up in Ollie debug. And Ollie debug detects that something's not quite right. We're going to load a script, which is an OAP finder. This helps us do it rapidly. Once it runs, you can see the top instruction there at address 40BB08, I think it was, is the actual original entry point. So basically, we paused execution at the entry point. We're going to dump this process from memory to a file so that we can try to analyze it. LordPE's dumped it for us. We're going to make sure everything is okay with the binary. Now we're going to rebuild the import table so that we can see what functions it imports and what DLLs. So this is import rec. We're getting the import table here. It's analyzing. So right there it's figuring out, okay, it's importing like socket and send and things like that. Now we're going to fix the dump that we generated from LordPE. And we're going to pop it open in IDA, and you'll see a totally different view of this binary than what we saw before when we tried to analyze the packed binary. So IDA's going to analyze this, and you can see already there's more information than there was before. This is the imports table, much more. You know, previously it had about 10 things. Now it's totally populated. You can see this thing modifies registry, does all kinds of stuff. It's a names window. You see here's a bunch of internal functions to the binary. And we should be able to see some valid instructions that make sense. So that's the manual process on an easy-to-do packed binary. It took a little while, so it can get quite tedious. Yeah?
So all of this should say is that you know, Val's really good at unpacking this stuff and manually debugging it, but as you said before, it takes a lot of time. We want to find a extremely generic way to debug, and if we can modify this to do everything automatically, then I can fire Val and save a lot of money. And so the solution should be pretty generic. I want it to work across a whole bunch of executables. It should be efficient, so we get good performance. Undetectable as much as possible. I don't want to say 100% undetectable. And extensible so that you can actually script things inside of it. So again, the algorithm is track the written memory. If that memory is executed, it's unpacked, and that tends to be a pretty good heuristic for doing this. So you have to be able to monitor memory writes and memory executions, and we want to automate the process. So the first technique we looked at was dynamic instrumentation. This allows a running process to be monitored, and you can set API hook points. The one that we used was Intel's PIN library. What PIN does is it uses a just-in-time compiler to insert code before and after an instruction. And what's nice about this is it retains the consistency of the executable. So if the executable goes to look at its own memory, it's going to find what it's expecting there. So you get good control of execution, instructions and memory accesses, and you can attach it to basic block. And what's nice about pin is that it allows you to attach and detach from the process. So normal instructions prior to pin looking at it is just like this. This is normal assembly. And pin inserts instructions before and afterwards, and that's where you can put your API hooks. And you can actually set trigger points so that you can do it on reads and writes of memory and actually on instruction execution. So afterwards, it looks like this. You have your instructions interspersed with pin instructions. So the two pin hooks we used were memory write and execute. We tracked the writes in a simple hash table. And if execution occurs on the written data, dump it. And the results were pretty successful. For the most commonly used packers, it works fairly well. These are mostly the packers that don't actually try to self-verify themselves, or they self-verify but do it poorly. And this is roughly 70% of all of our malware in our collection. For our collection of malware, which is fairly representative, we think, these are the packers that we saw used mostly. UPX and P-Compact are the top two. Armadillo, we'll ignore that one for now. FSG, ASPack, and ASProtect, round out the next one of them. So this works on all of those except for Armadillo. And just as a test or a proof of concept of this, we created a Hello World application, and then we graphed the results inside of a GDE, or the Go Visual Diagram Editor, which is a really good graphing package. So for the Hello World example, this is taking execution at each basic block and creating a little block with a memory address in it. And the idea here is, can we find the unpacking stub? Is it something that we can visualize pretty quickly? And the answer is that yes, a unpacking stub is usually a tightly coupled, close together set of instructions that should stand out. And if you look in the lower right-hand corner, there's a lot of connections between each of those basic blocks that are being executed. And so looking at this, you can see the addresses and find that the unpacking loop is easy to find. And it makes pretty pictures. It's good for wowing advisors. So the generic algorithm works well. It validated the idea. We verified all the addresses by manually unpacking it. And display clustering, that's also nice. And attach and detach is effective if you're able to monitor and say, okay, I'm going to be watched now. So Val will go ahead and demonstrate the dynamic instrumentation version of the unpacker.
Okay, so I'm going to show a short movie that demonstrates how this works. Okay, so in this case, we've got a copy of a piece of malware that's been packed with FSG. We're going to sort of run through some repetitive steps, but this sort of proves the whole process of what we're going through. This file is also executable. It actually works and runs. And so we're just making sure here that it's not actually running. Okay, so we're going to dump this obfuscated file into IDA and have it analyze it and see what we see. And this is sort of similar to the previous case. I think FSG is a slightly better packer than UPEX. But you're going to see the same sorts of problems. There's not much information here for us to analyze. There's nothing for us to look at. So the binary's been obfuscated. So in this case, we're going to run our tool rather than going through the sort of manual ollie debug LORD-PE process. It's going to run, and basically it's going to be tracking memory reads, writes, and executes. So here momentarily we should see a big pile of files that have been dumped. So our tool basically dumps these files automatically for you, and you can see the files are named, that they contain the original entry point that we guessed at in the file names. We're working on automating the import rebuilding process. We ran out of time for this demo, but we'll be there soon. So we're running import rec to rebuild this. And generally, it's going to be one of the first couple of dumps. And in that case, you can see this is the entry point we found earlier. So this sort of validates our process. Hey, look, we found the entry point automatically. So we're going to repair the dump with that particular entry point. Pop it open in IDA. And hopefully we'll see much better code that we can analyze. So I'm opening the file that was dumped and then rebuilt with import rec. And you can see it looks much better. There's valid instructions, there's names. We should be able to see functions internal. Blue is good. On the top there, that graph, the more blue, the better. So here's the internal functions. And the import table is fully populated. So if you have thousands of files, that's a much faster process for analyzing these files rather than the sort of manual, tedious figuring it out yourself. Here you can see valid assembly instructions. We can actually hop around. A sign of a well-deobfuscated file is, can I follow xrefs in the file and jump to different function calls? And in this case, we can. So it's been unpacked pretty well. And it works for most of the generic packers like FSG, the ones that Danny mentioned earlier. So you can see here we even have interesting strings that make sense in English.
Okay. The problem with dynamic instrumentation is that it's extremely detectable. Intel's pin actually inserts itself into process memory and actually will do a checksumming so that it'll come across these and basically find it. So signature scanning that's implemented in harder packers like Armadillo and T-Lock will find this. So we need to extend this to work generically and non-detectably. This method is also slow. It's roughly 1,000 times slower than native at best. And other methods and tools can be even slower. So we need a faster implementation. So we need some core operating system component that monitors all memory, intercepts those memory accesses, provides some method so that we can log it, and it's a fundamental part of the OS that the packer can't get rid of. So we looked at the memory management unit of the Intel processors, and we'll just go over a quick OS 101 for how virtual memory works. So in Intel memory, each process has its own memory, and you must translate that address from a virtual address to a physical address, or the address that's actually on the chip of RAM. And so for this, we're using non-physical address extension mode and 32-bit processors. So this is a 2-page index and then a byte index into the actual page. And again, each process has its own page directory. So if we take our virtual address, the first 20 bits are the virtual page number. Inside of that, using the CR3, we find an index into the page directory to get the page frame number. The second 10 bits get you the page table entry. And the page table entry is actually where we're playing our tricks with. And so this contains permissions and that sort of thing. And then actually, when you get that, you get the byte index into the page that's pointed by all of that. And so that's how the processor translates memory, and that's how the page fault handler will translate it. So all of these are hardware-defined data structures. And again, they contain permissions, whether they're present or been paged to disk. The page table entry also has this. It's the next layer down, and it has all these other bits which we can use to overload. So to speed all this up, there's a TLB, which is a translation look-aside buffer. And it resolves this as fast as possible and provides a cached way to look up addresses. And if it has a problem, let's say that there's a page that's not loaded in RAM, or there are incorrect privileges, or it's loaded but